All right, so we are going to talk about section 3.1 limits today. All right, so the first thing we have is a couple of definitions that are going to help guide us in what we can do with limits. So, the limit of a function. So, let f be a function and let little a and capital L be real numbers. Then we have two conditions here. As our x takes values closer and closer to little a from each side, and f of x values get closer and closer, maybe even equal to the value of L. And the second thing we have, the value of f of x can be made as close to L as desired by taking values of x close to a. Then we can say capital L is defined as the limit of f of x as x approaches a. So in other words, the notation we want to use is the limit as x approaches a of f of x equals L. This x goes to a means approaches. Or in other words, that arrow means approaches. So what we're talking about here is we're to have a function. We're going to try and pick x values that are close to sub value a. And we're going to get as close as we can to these values, these x values. And when we plug that in, we're hoping that we're going to start coming to a value of L. So the existence of a limit. So the limit of f as x approaches a may not exist. So we have to have some conditions that are going to guarantee us or help us determine if the limit even exists. So if f of x becomes really big or really small as x approaches a from either side, then we can say that the limit as x approaches a of f of x is equal to infinity or negative infinity and therefore does not exist. If f of x becomes really infinitely small as x approaches a from the right, so in other words, if we look at this is x approaches a with a positive sign on the right-hand side. That doesn't mean x approaches positive a. That means x is approaching a from the positive. And infinitely big as x approaches a from the left, so that means x approaches a with a negative sign, then our overall limit does not exist. Notice on this case right here, there is no plus or minus to the right of that a. This is the overall limit. What we're basically saying is in order for our limit to exist, or in order for our limit not to exist, I should say, then the limit from the left is equal to L, the limit from the right is equal to M, and we must have the condition that L does not equal M. If this is true, then our limit does not exist. So that's one way to always check and see what's going on. Take our limit from the left, take our limit from the right. So now we've got some rules for limits. We got these basic 8 rules that are going to guide us in everything that we do. So let little a, capital A, and capital B be real numbers, and let f of x and g of x be functions such that the limit as x approaches a of f of x is equal to a, the limit as x approaches a of g of x is equal to b. So in other words, we got two limits defined by capital A and capital B, and we've got little a basically being a constant. So if k is a constant, then the limit as x approaches a of any constant k is equal to that constant. And if the limit as x approaches a of k times f of x is equal to k times the limit as x approaches a of f of x is equal to k times a. Anytime that you have a constant that does not involve your variable, you can factor it outside of your limit and you'll be fine. The second thing that we can have, if we have the limit as x approaches a of f of x plus or minus g of x, we can break this apart into individual terms. So this would be the limit as x approaches a of f of x plus or minus the limit as x approaches a of g of x. Plugging in, we would get a, capital A plus or minus capital B. If we can add and subtract, then the next thing to look at is multiplication. the limit as x approaches a of f of x times g of x is equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x, which will give us a times b. If you got a product of two functions, you can take the limit of each one of them and then multiply the end result. If you have a division, the limit as x approaches a of f of x divided by g of x is equal to the limit as x approaches a of f of x divided by the limit as x approaches a of g of x, which is equal to a divided by b, where b is not equal to 0. The fifth one here, if p of x is any polynomial function, then the limit as x approaches a of a polynomial function is our polynomial evaluated at that a value. For any real number k, the limit as x approaches a of f of x raised to the kth power is equal to a to the k. So another way of writing this, if we were to take this step right here and come out here, we could have rewritten this as the limit as x approaches a of f of x all raised to the kth power. And then that would give us a to the k. If we can conclude that the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x, therefore we can drop our limits and we could say that f of x is equal to g of x at that point x equals a. We can't say this about everything else, but we can say that at that x equals a, they are equal. For any real number b greater than 0, the limit as x approaches a of b raised to the f of x is equal to b raised to the limit as x approaches a of f of x, which would be equal to b raised to the 8th power. So that's a lot of our theory that we can talk about. And then, how do we actually apply all this now? Well, let's get through a few more definitions first here. So number 9, for any real number b such that 0 is less than b less than 1, and the limit as x approaches a of log base b of f of x, we can bring that log outside to make this log base b of the limit as x approaches a of f of x, which is equal to log base b of capital A, assuming that capital A is greater than 0, because we cannot take the log of a negative number. So limits at infinity. Very similar. We have some rules here. For any positive number n, the limit as x approaches infinity of 1 over x to the n is equal to 0. And the limit as x approaches negative infinity of 1 over x to the n is also 0. So whether we're going to positive or negative infinity, we can use these rules right here and be fine. So to find our rules, our limits at infinity. If f of x is equal to a rational function, p of x divided by q of x, for polynomials p of x and q of x with q of x not equal to 0, then the limits x approaches infinity of f of x and the limit as x approaches infinity of g of x can be found in the following ways. There's two ways that we can do this. The first way, divide p of x and q of x by the highest power of x in q of x. Then we're going to use our rules for infinity up here, limits at infinity, to find the result from part 1 that we just did here. We'll see an example in just one second. So we're told, here's our first example. Let the limit as x approaches a of f of x equal to a, and limit as x approaches a of g of x equal b. Find the limit as x approaches a of f of x plus g of x. Well, if we have the limit as x approaches a of f of x plus the limit as x approaches a of g of x, then by plugging this in, our first one is capital A, our second one is capital B. So our answer is a plus b. There's nothing we can do to combine these. So on this next example here, the limit as x approaches 2 from the left of f of x is equal to 5. and the limit as x approaches 2 from the right of f of x is equal to -6. Well, one way to kind of think about this is write it like this. The limit as x approaches 2 from the left of f of x must equal our entire limit as x approaches a of f of x, which must equal the limit as x approaches a from the right of f of x. From the left, we are at 5, must equal our limit as x approaches a of f of x, which must equal -6. Well, this statement can never be true. 5 cannot equal the limit, which is also equal to -6, because basically what we're saying is, can 5 equal -6? No. So therefore, our limit, the limit as x approaches a of f of x, does not exist, or D and E. Now, we're told, find the limit as x goes to 3 of x squared minus 9 over x minus 3. So, the first thing that we want to look at every time whenever we have a value here is, can we plug in this value? Well, could we? So we get 3 squared minus 9 over 3 minus 3, which is 0 over 0. Anytime that you get 0 over 0 when you plug in, we need to think about some other stuff to see what we can do. All right, so obviously we could divide out, we could factor out. So let's start by trying to factor. So the numerator would factor to x minus 3, x plus 3 over x minus 3. X minus 3's cancel, so we would have the limit as x goes to 3 of x plus 3. Then we could plug in 3 plus 3 gives us 6. So in other words, our answer is 6. So first step with any limit, plug in and see what you get. If you get a number, 0 is a number, but 0 divided by 0 is not a number. If you get a number, it's your answer. If we don't get a number, we got to think about, can we factor? What else can we do here? So when we plug into this one, we get 1 over 3 minus 1 over 3 over 0. We get 0 over 0. So what if we, so in that case, what if we decided to take the limit as x goes to 0? Let's get a common denominator here. So this is going to be, if we cross multiply, we're going to get 3 times 1 minus 1 times x plus 3 all over 3 times x plus 3 all over x. And remember, anytime that we have a division over division, we can take that x and put it in the main denominator. So this is the limit as x goes to 0 of 3 minus x minus 3 over 3 times x plus 3 times x. So when we do that, we get minus x over 3 times x plus 3 times x. The x's cancel out, so we're left with the limit as x goes to 0 minus 1 over 3 times x plus 3. Now we can plug in 0. Negative 1 over 3 times 0 plus 3 gives me negative 1/9 as my answer. So looking at this one, so just like we talked about for limits at infinity, all those others were numbers. Limits at infinity have their own rules. So our rule said we're going to take the highest power of x in our denominator, which is this x squared right here. We're going to divide every term by it. X squared over x squared plus 2x over x squared minus 5 over x squared, all divided by 3 over x squared divided by x squared plus 2 over x squared. Simplifying, so we still have our limit as x goes to infinity. Simplifying, we get 1 plus 2 over x minus 5 over x squared, all over 3 plus 2 over x squared. Anything that still has an x in the denominator goes to 0. So we're left with 1/3 as our answer here. So again, we're going to do the exact same thing. We're going to divide everything by x squared. So 2x cubed over x squared minus x over x squared minus 3 over x squared, all over 6x squared divided by x squared minus x over x squared minus 1 over x squared. So this is the limit as x goes to infinity of 2x minus 1 over x minus 3 over x squared, all over 6 minus 1 over x minus 1 over x squared. This term goes to 0 because we still have an x in our denominator. Same thing with these other terms as well. So we're left with the limit as x goes to infinity of 2x over 6, which will reduce to x over 3. Now, when we plug this infinity in here now, we get infinity as our answer. So we have to keep that in mind that we could still get that as an answer. So going back to our numbers here, again, limit as x goes to 25 of square root of x minus 5 over x minus 25. If we plugged in 25, we would get square root of 25 minus 5 over 25 minus 25, which is 5 minus 5 over 0, or 0 over 0. All right, so now we have to look at this one and say, all right, well, how can we factor this? Well, I don't know how to factor this, is what most of you are probably saying. So let's think about this and let's do this a slightly different way. There's no way we can easily factor this. But since we have a square root of x in our problem here, we're going to multiply top and bottom by its conjugate. And the conjugate here is the square root of x plus 5 over the square root of x plus 5. So we get the limit as x goes to 25. No need to multiply out the bottom. You can just make it x minus 25 times the square root of x plus 5 for now. When we FOIL out the numerator, this is a difference of squares, or difference of conjugates here, a minus b, a plus b, which will give us x minus 25, because we know a minus b times a plus b gives us a squared minus b squared. From here, we can cancel these out, so we're left with the limit as x goes to 25 of 1 over square root of x plus 5. Now we can plug in. So we get 1 over square root 25 plus 5, which is 1 over 5 plus 5, or 1/10 as our final answer. Now, so we're told we got 3 different things we're going to end up finding here. So we're going to use the limit as x goes to 4 of f of x is 12, and the limit as x goes to 4 of g of x is equal to 8. So that's our 2 givens, or our knowns. Well, now we're going to use that to find these 3 things. So the first thing, the limit as x goes to 4 of f of x divided by g of x is equal to the limit as x goes to 4 of f of x divided by the limit as x goes to 4 of g of x. So that's going to be 12 divided by 8, or 3/2. Next, we could have the limit as x goes to 4 of 5 times g of x minus 1 over 1 plus f of x. Easiest way to do this is to plug in. But if we want to do it this one way, we could say the limit 5 times the limit as x goes to 4 of g of x minus the limit as x goes to 4 of 1, all divided by the limit as x goes to 4 of 1 plus the limit as x goes to 4 of f of x. So remember, limit for g is 8, so this is 5 times 8. Limit of a constant is just the constant, so over minus 1 over 1 plus 12. So we get 40 minus 1 over 13. So 39 over 13 gives us 3 as our answer here. The last one we have is the limit as x goes to 4 of the cube root of g of x. Well, by our rules, we can take this cube root of the limit as x goes to 4 of g of x is equal to the cube root of 8, which is 2 for our final answer here. That kind of gives us our good foundation for limits. We will continue using limits in the next section as well, but that's all we have for this lesson.